My name is Pradeep Kumar. I am the Oregon chair for the ComSoc Society here locally, as well as the director of ComSoc Region 6, which is the Western region. Today on the call, we have a number of ComSoc chapters across the West Coast that is co-host today. We have the Seattle chapter, the Vancouver, British Columbia chapter, Santa Clara Valley, the Foothills, San Diego, Buenaventura, Orange County, Sacramento Valley, Austin, and as well as the Oregon Computer Society. Thank you all for being here, and I see a large number of people on the call. We normally meet at 5:30 on the evenings, and we had to do something different because our speaker is calling in all the way from France, and it's at 9 o'clock for him at night. So we decided to try a lunch speaker series today. Our moderator is Rath Vanathambi. He's our vice chair for the Oregon chapter. He's also a senior scientist with Intel and an editor of the IEEE IoT magazine, as well as an IEEE fellow. So at this point, I will hand over to Rath Vanathambi, who will introduce the speaker.
All right, thank you, Pradeep. So I'm very happy to introduce our speaker and my colleague, Dr. Laurent Cariou. I'm sorry if I don't say your last name, Laurent. Okay, so basically Laurent was in Oregon, but recently he moved back to France. Laurent earned his PhD in electronics from National Institute of Applied Science in Rennes, France in 2006. He has spent over a decade working in IEEE 802.11 and currently serves as Intel's principal engineer and technical lead for mainstream Wi-Fi 802.11. Laurent played a key role in establishing the high efficiency wireless LAN. It's also called HEW, H-E-W, group that eventually led to the development of 802.11ax and Wi-Fi 6. Recently, he also initiated the Extremely High Throughput EHT activity. Currently, Laurent holds the position of the vice chair for the 11be BE or EHT task group, also Wi-Fi 7. Laurent is also the chair for the next generation ultra high reliability UHR, which is going to be, Wi-Fi 8 study group as well. So it'll be no other best way to hear from 11BE and also some introduction to the next generation UHR or Wi-Fi 8 kind of activities from the chair himself. So without any further ado, let's hear about these new technologies and the next generation from Laurent. Let's welcome Laurent.
Okay, thanks, Russ, and thanks everybody. Thanks, Pradeep. Okay, so yeah, let's have a quick introduction to 11BE. I probably won't be able to have a lot of time to go into the detail of it, but I'll give you a sort of big picture on the objectives of the group and the different high-level features that we did define. We're still sort of in the process of defining it for this program. So, okay, yeah, that's switching now. Okay, let me put that just on the side so I'm seeing the slides properly. Okay, so this slide is just showing, the different generations of Wi-Fi. We started naming them with numbers really with Wi-Fi 6. So we went backward after to name it Wi-Fi 4 and 5. Well, nobody was using that at the time. But anyway, Wi-Fi 4 is kind of the code name of in 802, which is 802.11n. 5 is 11ac, and Wi-Fi 6 then was or is, that's really the one that's in the market right now in the new products that are coming. Which is 11ax. And so obviously throughout the different generations, there's been enhancements of mostly throughput driven at the very beginning and more with the penetration of Wi-Fi into many different type of devices, different usages. Obviously, had to diversify also to take into account other aspects like, that's security, or that's reliability, latency, and those kind of things. So, progressively evolving a bit towards a more diverse type of objectives. But yeah, to summarize quickly, Wi-Fi 4 11n was mostly, that's where we started seeing 5 gigahertz band support. Before that, it was mostly 2.4 gigahertz. It took a bit of time before 5 gigahertz actually, so rural penetration and devices. Wi-Fi 4 was, 11n was also mostly, 40 megahertz operation at 5 gigahertz. It was allowed through it, and MIMO got brought in. So it really started with MIMO, I guess, getting to 2x2. And with Wi-Fi 5, which was 11AC, then we started really, because Wi-Fi 11AC was only operating at 5 gigahertz, so it really gave the momentum to start moving away from the 2.4 gigahertz band and to take big benefits of a wider channel and wider bandwidth that was available in the 5 gigahertz band spectrum. And that was kind of the main solution. We also increased the bandwidth. 80 megahertz, 160, there was mu-MIMO, but it's been used, but mostly the gains were through the very easy stuff, which was to increase the bandwidth, and that was allowed with that new band. And so with 11ax, we started trying to look into more, we're penetrating now stadiums, dense deployments, and so we focused a little bit into making sure Wi-Fi would be performing well also in this very high density environment. And so we introduced this multi-user operation, which was obviously used in the cellular space before that. So that's obviously well-known technology with OFDMA, both in uplink and downlink, and that kind of triggered or colored that generation. Around the middle of this project, there was also on the side an effort by the community to push for opening a new and licensed spectrum at 6 gigahertz. You probably have heard of that. And so by, as I said, kind of in the middle of it, we introduced a way to operate also 11ax in that new band, which was obviously a huge opportunity. And that's under codename Wi-Fi 6E. If you've seen that a bit on the field, products are starting to come with that, and obviously, we moved with Wi-Fi 5, 11AC launched around 2013 to enter the 5 gig band, starting to see a bit of saturation into this, and so we now exploiting this new huge spectrum that's available at 6 gigahertz. With Wi-Fi 6E, which has been launched basically January 2021. So that's kind of where we are, or where we were at least at the beginning of BE. And so 6 and 6E, which obviously this is kind of the marketing slide. Obviously, this is all the enhancement and improvements that you can see with that. There was throughput improvement to some extent, but mostly more efficiency in the operation with multi-use operation. And so on. And obviously the 6 gig band is really gonna, I think I've got a slide quickly on this one, but the fact that we have this new spectrum where nobody is really operating on, at least on the unlicensed spectrum. So this is still a band that's occupied by some other, by some incumbents. There's some kind of point-to-point links that are used by some incumbents. So there's been some regulatory rules that's been put in place to allow Wi-Fi to operate without interfering with those incumbents. And there are different modes where you would have a limit mostly limiting the transmit power. But we've got also more enhanced mode, which are really using database, like they call it this AFC mode, where based on your location, you would know if you're allowed to transmit with a slightly higher transmit power without interfering with the incumbents. but we end up with 1.2 gigahertz of spectrum in the US, half of that in Europe, and throughout the world. It's spreading more and more. We just have probably in China, which is still still lacking some penetration there. But anyway, so huge bandwidths available at 6 gigahertz, and everybody's obviously jumping on that because that's a great way to get very good performance when you don't have to share the medium with others. And obviously, as the bandwidth is much larger, like the band is larger, we can have also a larger channelization, which increases the bandwidth and the throughput pretty easily. So hopefully, we'll see that penetrate progressively in the market and spread on the different environments, and that's likely going to be a great thing. Now, Wi-Fi 7, we started that, I would say, probably 4 years ago now. We're trying to progressively go into a phase of one generation every 4 years. And per generation, we do typically 2 releases of products. There's the release 1 product, release 2 products, and then we move to the next generation. That's a bit where how we start to do things. And so every 4 years, we need to obviously gather in 802.11 and think what will be potential features that we can implement, what's available on the features on the PHY and the MAC layers, and what is the demand, what's the objectives in that sense. And obviously, the fact that we just opened the 6 gigahertz band really opened up the possibility to increase the bandwidth. So it was, we went kind of back to the origin, was very simple, throughput-oriented objective. We see the goal in the project, call it the PAR. That's the document that defines the objective of the program, which about 30 gigabit per sec at the max app. So you see something that you won't see in the products really, especially on the client side, but basically it's kind of doubling the throughput compared to the previous generation. If you are implementing all the functionalities that is allowed by this, it's actually we'll be able to do more than that. Even in the early products, we'll see. So a lot more that probably you need today, but a great way to have a generation which is much better than the previous one. And we started looking really into the latency and jitter, this worst case latency, with the AR/VR type of applications starting to grow. 4 years back, it was still pretty up in the future. And we'll see that when we talk about Wi-Fi 8, which is a new UHR situation, program, sorry, that this objective of latency and getting predictability in the transmission of high QoS traffic is going to take the majority, and we're progressively moving away from very raw throughput increase towards more qualitative QoS enhancement. So Wi-Fi 7 is kind of in the middle between those two things here. So anyway, so this is typically those project objectives are pretty open, pretty simple, so that we get the consensus in 802.11. There's a lot of actors there. You probably know how all this works. And it's very open standard, so everybody can come and contribute, and we're just voting to progressively make the decisions and build the spec. So we obviously start with a pretty wide objective, and then progressively we define the features. So the key enhancement that will constitute Wi-Fi 7, it's basically going to be 320 meg channelization. So we were up to 160 megahertz, and we'll double it to get to 320 meg. And that obviously was not possible at 5 gigahertz because we don't have enough spectrum. But now that we have the 6 gig band, that becomes possible. So it's a relatively easy solution. As usual in a standard, you increase the bandwidth and you increase pretty much everything. That's been kind of the key enhancements or the low-hanging fruit every time. obviously there's some complexity associated to it, no questions, but that's typically the lowest hanging fruit for solution. We did define also 4K QAM. We were getting close to the limit also to what we are capable of doing. We were doing up to 1K QAM modulation in the previous generation in Wi-Fi 6, 11ax. And so we went to 4K QAM. That's probably going to be where we end. I don't think we'll go to 16K QAM, sorry, in the future, unless there are some very strong enhancement or improvement in how we deal with that. But so far, you already need to be extremely close to the transmitter and receiver to be in the condition where that can work. Multi-RU, and I'll go a bit more detail into those features, but this is a high-level description. The RU here, that's the resource unit. That's the name we call the allocation, the number of subcarriers in frequency that's allocated to one station when we do multi-user operations. So when we do OFDMA, if you've got a 320 meg bandwidth, we're going to divide that into multiple RUs in frequency and give one RU, one big, one small RU to one stay, and the rest to other stays. It was always one RU for one stay in previous generation, and obviously that RU size could be of different bandwidths. Could occupy the entire available bandwidths, or or smaller. So different bandwidths per station. Here now we are allowing multiple RUs to be allocated to one stay, and the goal is to, and I'll show that, is to have non-collocated RUs that's allocated to one stay. I'll give you some examples of why this is of interest in there. So those are the there's kind of the three main file layer enhancement that have been defined. And on the Mac side, there's obviously all the mechanics to enable those modes to happen, which is a very straightforward thing to do typically. But we've worked a lot on the multi-link operation and the ability to be able to operate simultaneously, or alternatively, all the flavors are possible on different bands at the same time. So you can be a device that has a radio at 5 GHz, a radio at 6 GHz, and you can obviously with that increase either the throughput, the latency, or what you name it. So you can call it multi-band, whatever. We called it multi-link for specific reasons in the naming in .11, but that's the idea behind it. And we've worked a bit on the deterministic low latency. Obviously, some of them, are gotten kind of for free with this multi-link operation, or through the enhancements in the file layer. But we've defined also what's called a restricted TUT. I'll have a slide on that to show you very quickly what that entails. So yeah, overall, those are the key points. Obviously, there's a lot more details to it, but those are the key solutions that you'll see in that program. And so just before I enter the features themselves, so just so that we see where we are on the timeline. So 11be is now in the phase where so we are the draft 3.0, 3.1. Just a year ago we produced the first draft of the standards, and now we're in the phase where we resolve the comment and draft after draft. We read the spec, collect all the comments, and fix all the issues that everybody notices. So we're not bringing new features really at this stage now. It's becoming pretty stable. We just make sure that the spec is very solid and everybody is agreed on fixing all the bugs of the standard. And so this is going to continue because it takes a lot of time. But at the same time, obviously, in some other organization, there's the certification for those Wi-Fi 7 devices, and different profiles of it are being done and defined. And so the expectation is by the end of this year, 2023, we'll see certified products being in the market. There's probably already some early implementations out there, but you'll see certified one happening at the end of this year. Okay, so very quickly on the PHY enhancements. So this is kind of the figure and illustration of the physical layer of a packet, PPDU, which is sent in Wi-Fi. There's the preamble, and the preamble obviously gets bigger and bigger every generation. And there's the payload where you carry the data. What we did is we kept before that to always have tricks. We were not really forward compatible when we were defining the preamble. So we're always finding tricks to make sure that legacy devices would be able to understand the first part of a packet, even if that's coming from a new generation, and have some ways to differentiate between, for new devices, to differentiate between a legacy packet or a Wi-Fi 4, Wi-Fi 5, Wi-Fi 6 packet. And we ended up with tons of tricks, which was a bit ugly in the end. So this time now we fix it and make it clear. We've got this, what we call this universal SIG, called USIG. And with that, we've got very explicit signaling, which defines a generation. So it's very easy now to determine, based on actual explicit data information, what generation the packet will be on. So we should have done that a long time ago, but unfortunately we didn't. So at least we're fixing it now. And so that's going to become useful and helpful in the future if we're building also generation after Wi-Fi 7. So more on the feature, I mentioned this 320 megahertz channelization. So I'm showing here, it's a bit small, but that's the channelization at 6 gigahertz. So it's the band that goes between 5.9 to 7.125 here. And so you'll see the different channels. So you've got 60 20 megahertz channels. So you can imagine the amount of bandwidth we get compared to 2.4 gig band. In 2.4 gig band, we only had 3 non-overlapping channels like this. Here we've got 60. So we can obviously do 40, 80, 160, and now we're defining this 320 megahertz channels. And so we're favoring obviously non-overlapping channels, so there is no interference between channels. And so we'll be able in the US to get up to 3 channels that are available. And it is still a little bit too short for an enterprise deployment. Like they typically want to have a deployment with frequency reuse of 7 to 9, something like this. So they're probably going to use 160 megahertz, which is still a lot more than they use today. Probably stuck at 40 or 80 megahertz today. So here they'll be able to do this, but opportunistically, if they want to use 320 or in home network, if you want to use 320, you'll be able to use it. And obviously by doing that, you'll get a lot more throughput, which is done there. So, no magic here. We basically just extended the bandwidths and use the same mechanism for channel bonding that we were using before, and stick to that concept of staying with non-overlapping channels. Yeah, multi-RU. So I did mention that. So it's the ability to allocate to one station or one BSS, one cell, non-colloquial is not the right term, but disjoint frequency allocation. So the use case, the main use case for it, it's really going to be at 6 gigahertz, because we've got incumbents. I did mention that, right? We're using that band, which is already owned by some incumbents that have paid a license to operate there. So they obviously need to be protected. So there are some modes where Wi-Fi will transmit very low power, and they're just going to ignore incumbents, and they can transmit wherever they want. But there are modes where Wi-Fi can transmit at a higher level of power, which is equivalent to what to the power they can use in the 5 gig band. But they need to, as I said, right, look at the localization they are in, and the database is going to give them some channels on which they are allowed to transmit and some channels on which they're not allowed. And so here we've got an illustration where in the orange section here, there would be an incumbent, and so the Wi-Fi is not allowed to operate or transmit, and same thing here. So what we can do if we want to use, for instance, 320 megahertz channel and transmit on both sides of it without transmitting on that orange allocation, we'll be able to do it with this multi-RU solution, which you can call a puncturing mechanism, right? It's a puncturing solution, and especially the one which we call static puncturing, which is going to be static for the duration, because the incumbent is not going away. So again, so kind of.
Will you provide the slides?
Sure, yeah, I can provide the slides. Yeah, no problem. Yeah. I don't know if I need to share it beforehand, but I'll be able to share afterwards. Yeah.
Thank you, Laurent. Yeah, you did not need to share it ahead of time, but yeah, thanks. The audience asked that question. I usually ask this question at the end. Yeah, thank you. Yeah,
no problem. Yeah. And don't hesitate to ask question. Obviously, I can see something on the chat, but I don't know if I'm not seeing the chat window here. Okay, so anyway, so yeah, we've got ways now to transmit on both sides of an incumbent. We could also be a bit more dynamic. If somehow one channel becomes unavailable because there's somebody else also another Wi-Fi element, we could be able to do this, but early products won't be able to be very dynamic. So, but the static operation here, particularly fit for 6 years, is going to be a good fixture to get. And the puncturing granularity is only 20 megahertz, so it's per 20 to keep it very simple and that is an illustration of the data rates, kind of the PHY rates that you're going to get, and the comparison with what you get with Wi-Fi 6, and what you get with Wi-Fi 7. And so, maximum was 10 gigabit per sec, and we're getting to 23 gigabit per sec per link. And so we'll be able to do multi-link on top of that. So possibly not doubling it, but at least doing possibly 1.5 over this with Wi-Fi 7. That's more of an illustration of what the client will experience. Typically, they have either 1 or 2 antennas, so 1 or 2 spatial stream, and so depending on the modulation, that's the order of data rate that we're going to get. So you'll see products with 5, 6 gigabit per sec announced, and a very stable gigabit per sec operation. So we're getting closer to the 10 gig per sec target, but we're not quite there yet. So yeah, so that's the thing. So yeah, so that's most of the physical layer enhancements. And so on the Mac side, the key feature, and you'll probably hear that a lot as the feature representative of Wi-Fi 7, and that's called multi-link operation. We call it MLO, and that's basically a concept where so you see the figure on the side here. Imagine that this is the AP side on the top and the station on the bottom. Typically, APs on the field today, in the AP box, there is actually 3 APs. There's one AP operating at 2.4 years, one AP at 5 years, one AP at 6 years. And the client, same thing. So it has the ability to operate at 2.4, at 5, at 6 gigahertz. Either it's just one stay on the client side, which can do one at a time, or it can go and operate on each other's band, or it already has 2 radios being able to operate on 2 bands at the same time. So we continued through that aspect by now merging everything within one device, both on the AP side and on the client side. So if the AP here in the top has 3 AP actually on 2.4, 5, and 6 years, we will call it now a multi-link APMLD, an APMLD, AP multi-link device. And the multiple stations on the client side, we call it a non-AP multi-link device. And now we're going to basically, instead of having just an association between one stay and one AP, and that being the only link that's possible to use at a time, we're going to now make an association between at the device level. So basically this multi-link, this APMLD will get associated to the non-APMLD, on the contrary. And by doing that, multiple links will be able to be established, and you'll be able to either switch seamlessly between one or the other without needing to reassociate and renegotiate all the parameters. Or you're also going to be able to transmit jointly on multiple links to increase the throughput, right? So you can operate with 160 megahertz at 5 years plus 160 megahertz or 320 megahertz at 6 years, and be operating jointly at the same time if you have the capability to do it. And APs typically do have that capability today already. If they are tri-band APs operating at 2.456, they can operate at 5 and at 6 without interfering each other. They've got built-in filters that make sure that they can operate without any interference. On the client side, it's obviously more complicated to do. So we've looked into many different scenarios and cases to get all the wide spectrum of device complexities. The high-end device will be able to get multiple radios. The low end will get just one radio, which is able now to move between links seamlessly. And so by doing that, yeah, you can aggregate the throughput between links to increase the throughput. You can increase the latency, by competing for the channel access on both links, or 2 links or 3 links at the same time, and the one on which you get the first, you'll be able to transmit on this, which will reduce the latency or increase the probability that you'll be able to successfully transmit on those links. So great enhancements depending on the use case and KPIs you want to fill in. You're going to get that. So that obviously it's a big change in the architecture. So we had a lot of discussion, and the spec is pretty big on that aspect. But in the end, the concept is pretty simple. It's just being able to do this. And obviously a lot of changes and different flavors that you'll see with multi-link on the field. And that slide is kind of illustrating the different flavors in terms of kind of order of complexity a bit on the client side. So the AP set would always be, if it has 3 APs in this APMLD 2.456, it will have to be able to operate with 1 radio for each of those APs, and to be able to operate independently on each link compared to the others. On the client side, it's different. We're going to have what we call multi-link single radio. So it really is a device that just has 1 radio. It can establish 2, 3, 4 links with an AP. So it can be able to operate at 2.4, 5, 6, whatever higher number of links that it has. But it has only 1 radio. So if it wants to use all those links, it will obviously have to multiplex in time the usage of it. So you'll be able to operate to 4 for a while, then go to 5 and operate, go to 6. Everything will be fluent and transparent when it transitions, but there's this constraint in radio. So the throughput obviously with this will be a bit reduced, but you'll be able to get latency benefits or a lot more flexibility for load balancing in dense environment. Then we've got let me jump in directly to the dual radio, get a little back to the EMLSR after, but dual radio, you get the point. It's pretty easy. You've got 2 radios now. So you'll be able to have 2 links in parallel, 1 at 5 gigahertz, for instance, and 1 at 2.4 gigahertz. And they are able, and they're not interfering with each other because you've got good filters between themselves. So one can transmit, the other can receive without any problem. And so you'll be able to then transmit either the same thing or differencing or whatever you want to do, but you can increase the throughput by doing that, or latency and so on. So those are obviously more high-end devices because you need 2 radios and you need to make sure that they don't interfere with each other. And we call this STR, so simultaneous transmit and receive. And we've got the non-STR, it's the non-simultaneous transmit and receive. Those are the ones that are 2 radios, but they interfere with each other. So if one is transmitting, it's going to basically leak some energy to the other radio and make it become too much interfere to be able to receive something. So it's a radio with constraints, and obviously the performance of that reduces quite a bit. So typically that's what you'll see between 5 gigahertz and 6 gigahertz. If it's a client that has that wants to do a radio between those 2 bands, it's hard, or it's kind of complex to have filters between those 2 bands here. So you'll typically have those type of devices. And so the enhanced single link multi-link single radio (EMLSR) is an attempt to then find a good trade-off between complexity and the gains you can get with almost like you had an additional radio. So it really can only use 1 radio for data high-speed transmission at a time. But when it's listening to the medium or in very kind of light receive mode, it's able to have 2 light radios or 3 or more. So it's really able to kind of wait and listen on 5 and 6 gigahertz jointly at the same time. And so if the AP starts transmitting to that stay at 5, because it's the fastest channel that got used, that it got access to, it's going to send a signal to wake up that link specifically. And so the client will then power up the full radio on that channel. So it's a way to, you don't increase the throughput per se really by aggregating, but you're much more able to wake up the right link depending on what's available and have the ability to wake it up. So you see, we went through pretty much all the different flavors you can imagine depending on the devices. And so you'll see a very cheap device with just single radio. Probably the core will be EMLSR, and then you'll have some very small high-end type of device with STR operation.
Laurent, there was a question in the chat
Yeah.
window. Maybe I can quickly say that, basically the audience asking for, is the specification support a multi-link operation in 6G low band and 6G high band?
Yeah, good question. So I mean, the spec allows it, obviously, right? The spec doesn't preclude anything. We've got all the mechanics to make it work. Now it's a question of how you'll be able to build filters to sufficiently isolate the lower part of the 6 band from the higher part, so there's no leakage and interference between the 2. And again, the requirement on the AP side is that shall not have any leakage. So the interference that's leaking from one band to the other shall not be above a certain threshold. So that's regulated pretty clearly. So an AP will have to be very, very clear on that. But if it's able to build that filter, it's going to be able to do it without any problem. On the client side, there is this NSTR, non-STR mode, which allows some leakage and have operation that works even without leakage. So it's easier, in a sense, to operate between low band and high band. But yeah, no limitation. The spec can allow, So we likely in the early days we won't see that too much, but progressively, as the filters get cheaper and people invest more into those modes, we'll be able to see maybe 3 band AP, then 4-link APs, 5-link APs, 2.4, low 5, high 5, low 6, high 6. We'll see if that comes in the future.
Thank you. So one other follow-up question, when you were showing those KPIs, you mentioned, when you have 2 chunks of that spectrum, maybe you can get double, or not actually double, maybe 1.5 something. So why is that? Is that because of the interference issues or something else?
Oh, why you don't get 2 times? Just one? Yeah, just because to get 2 times, you would need to have the same bandwidths and same parameters on each link. but we can't get 320 megahertz link at 5 GHz. So basically, probably the biggest, like the highest you can get is 320 meg at 6 GHz plus 160 meg at 5. So it's kind of 1.5.
Okay.
But if you can do 160 plus 160, in a sense, you're doubling your throughput, and so you do times 2. And now obviously, there can be some slight limitation because of the protocol, but generally speaking, you'll be able to multiply that.
Thank you.
Okay, see the time flying pretty quickly. So anyway, so you understand. So I'll skip that thing. So you've got, obviously, we built a tool for discovery and association at the multi-link level. As I said, you can move from one link to the other in a very seamless manner. Let me just quickly here separate from multi-link. Obviously, if you've got more questions, we can come back to multi-link, but I did mention latency oriented, and we started doing a few things on latency. Obviously, as you can imagine, the multi-link can handle some of the legacy aspects already, and that improves this. We did define a mechanism, though, for per link to try and improve and better protect or better ensure that some prioritized traffic gets more chances to access the medium in some cases. So in 11ac, we did define what we call target wait time. So it's a service period in time that's negotiated between an AP and a stay to determine, again, a service period during which the two are going to interact. So it was mostly for power save. So it'll be power save outside of that period, and during those periods, the client wakes up and the AP will transmit, or the stay will transmit to the AP. What we did with that is add this, what we call now restricted TDRT. And so we added just one very simple requirement. So if a station has a very high priority traffic, downlink, uplink, whatever, imagine an AR/VR application, or you name it, it's able to negotiate with the AP a particular service period for this. So it knows exactly when the packet is supposed to come. It's going to define an RTOT for that time, and the AP is going to advertise that in its beacons and say, this is the service period which is for that application, and I'm making it restricted. And so all the stations that see that will have to now end their ticks up. If they were basically on the medium sending frames, when the start time of the service period comes, they'll have to end it so that there's a contention period that the AP can grab the medium to then schedule the high priority traffic. So that's the very basic concept. So basically, you define a specific period of time, and you make sure that if the medium was busy before, when that time comes, you have to release the medium and let the AP get it. I'm simplifying it in sort of terms. Obviously, it's not exactly how it works, but that's kind of the idea behind it. Unfortunately, this is an optional feature, so we'll see some devices that don't respect it, and that is supposed to work really if everybody implements it. Hopefully, in some environments, we'll see all the devices supporting it, and obviously, it's a very like automation type of environment. IoT, you can see that all the device will support it, and there's a good momentum on that feature. So hopefully, this will help a lot ensure the QoS, which is often seen as a weakness for Wi-Fi, but progressively, this is really improving over time. If there's no questions, I'll move to just the introduction of Wi-Fi 8. But let me know, Russ, if there's some more.
There were a couple of questions. One is on how much self-interference cancellation required to operate simultaneous transmit receive.
Yeah, good question. So the requirement is that the CCA, what do we call the CCA, is the clear channel assessment of one AP on one link doesn't get triggered by a transmission on another link. So you've got two APs, one at 5 GHz, one at 6 GHz. If the AP at 5 GHz is transmitting something, we're going to measure what's happening at 6 gigahertz. And remember, we're doing Wi-Fi. It's a listen before talk. So you're always listening, checking if the medium is busy or idle. And if it's idle, then you count down and you're going to end up transmitting. So you do this CCA, which is the way to determine if channel is busy or not. And so we've got a threshold, which is minus 82 dBm, which is the level of energy per 20 megahertz, above which you consider the medium as busy and below which you consider it as idle. So we kind of using that threshold to consider that. So you basically, if you transmit on one link, you shall not consider it as busy on the other one. Otherwise, you're stuck. Now, in reality, if you are putting energy up to minus 83, minus 83 dBm, so you're slightly below it, you're still going to impact quite tremendously that thing. So if an AP really wants to make sure things are going to work properly, it would probably be, need to be a lot more conservative than that, and probably ensure that there's no leakage, below close to minus 100 dBm or something like this. But this depends on what the spec defines and what products will have to comply to get good performance. But that's more or less, what is the requirement.
Thank you. One other question in the restricted TWT. So basically, the TWT is TXOP is given, and then take it back by the AP. It wants to do the high QoS, to support high QoS, given and take it back, something like that, right?
Yeah, it's a bit like this. It's it's typically kind of distributed, right? There's contention period kind of regularly. Everybody can compete for the medium. Some station will get it. The AP will get it sometime. But the idea is that we define a particular time. If one stay, on the side that's not related to this low latency traffic, gets the medium a little bit before the TWT-SP and wants to keep going, it got it 1 millisecond before, and it would want to do 5 millisecond TXOP. It won't be able to do it at, when it hits the boundary, it will have to, okay, I'm stopping, I need to close my TXOP and open a new contention period, basically, where everybody can compete. And the AP has favored access to the medium, so it's got a lot more chances to get the medium. So that's kind of a way to give it back to the AP. That's the idea behind it. So it's a bit the way you explained it, but with the rules that apply to Wi-Fi.
How do they know? The restricted TWT window, is that
so that's going to be that's going to be advertised in the beacon frame of the AP. So it's relatively static. So it has to be for a very predictable traffic.
Then it's okay. Yeah, right.
Yeah. Then it's okay. If it's more opportunistic, then we are we're not fixing that, at least in this generation. We'll look into Wi-Fi 8 for that use case. Yeah.
I have a question.
Yes.
About energy proportionality. In 11BE is access point or the client energy proportional, or they are not? And by when I say energy proportional, I mean the AP or the client consume power even if there is no traffic going on. Like the access point, you put it up, still consume energy even if it doesn't receive or send any traffic. Same for client.
Right. Okay. So that goes into the power consumption. I guess that's what you mean, really.
Yes.
Right. Yeah. Yes. Yeah. So there are. Obviously, power consumption has been a huge interest in Wi-Fi over the generations, and that kept on improving over time. Mostly focusing on the client in the past, and so far, because obviously clients are battery powered, so it was a lot more. There's a lot of constraint out there while the APs were plugged in, so it was less of a concern in the early days. But the clients, they're typically they are able to go into different state level, a state where they are very active, and they consume a lot. That's what they use when they transmit and when they sort of need to receive something. And then they can go to a DOE state, and that different level of saving powers, obviously, depending on the clients.
When it is not sending or receiving any traffic, does it still consume energy?
I mean, that depends on the implementation, obviously, but yeah, if it's in DOE state, when it doesn't receive and it's blind completely, it's not operating, it can consume very, very, very low level of energy, if not no energy.
The reason I'm asking is that in wired networks like in router and switches and line cards, they still consume energy when you boot it up. Even 90% of the energy is consumed by just booting it up, and as traffic started to be sent and received by the line card, it will consume more energy, which is proportional to the amount of traffic you send or receive. But still, that percentage of energy consumed to forward traffic or receive traffic is less compared to the energy that is consumed by the line card when you boot it up. So I wonder if the same thing applies in wireless LAN for the access point or for the client.
Yeah, I probably won't be able to have a very clear answer to you on this. For sure, there is, those two aspects that are there. I wouldn't be able to answer to you properly on the proportional between those two. But what I can tell you for sure is that there are enhancements that are done to try and lower the consumption everywhere.
Laurent, I think we have 5 more minutes. Maybe you may want to, cover a little bit on the Wi-Fi 8, and then, if you have few minutes, we can go over the rest of the questions. Thank you.
Yeah, no problem. Yeah, I can do that, and I can be pretty brief because Wi-Fi 8 is just at the starting point now. So we started discussing on this like a year ago. We created a study group called UHR, and we just actually agreed on the objectives in March. So last month in the 802.11 meeting. So the next program will be called 11BN, if you want to know it in advance. But it's going to be on the market with the name Wi-Fi 8. And so the trends, as I mentioned, was more XR, more latency-driven type of application, more peer-to-peer links. And the candidate features that we're talking about is multi-AP coordination, getting more, more coordination between APs, either at home or the enterprise. Enterprise, they've done it for a while, but you can enhance a bit what they're doing there. And a bunch of features, especially on the Mac side, in order to improve this deterministic latency. So trying to get more predictable in this kind of in the sense of what we're doing here with R2T, but going a bit further with the preemption, talking about those type of things that will make it happen. And so we had a project will start. Well, the task group will start in November this year, and we'll go for 4 years pretty much. The goal is to get, as I mentioned, 4-year cadence. So by the end of 2027, you'll see first certified products hitting the market with this. We had a lot of debate on millimeter wave, which is the operation at 60 gigahertz. We've got a 60 gig unlicensed spectrum. There's already been attempts in the past to try and operate in those bands, which is not an easy band to operate on. It's pretty complex to do. But obviously we're starting to hit a bit the limit in terms of very easy enhancements we're doing in the lower band. And so we've got this big spectrum available with something like 7 gigahertz of spectrum available in that portion. So it's a great way to get those latency and throughput application running, even in dense environment, through that band, if we were able to do it. There was a lot of discussion in the group. A lot of companies were in favor of that very strongly. Some more conservative were thinking it better to wait for next generation. We ended up agreeing on a dedicated program separate from it, which is going to be called IMMW for Integrated Millimeter Wave, and which is going to work on operating in the millimeter wave for the future of Wi-Fi. And so, that's going to hopefully give some momentum to that as well, because in the future, we need to prepare for enhancements of Wi-Fi for generations to come. And obviously the spectrum available in those bands is so huge that we can't avoid that and ignore it. But yeah, the goal is going to be a bit different than the way we did it with previous generation on millimeter wave, and it's going to be to basically reuse and define the very core minimum. Basically, almost take the radio you had in 2.45 and 6, upclock it, and make it operate at 60 gigahertz, and to be able to do that. So that's a program that's going to start. This is going to be the timeline we have. So we'll have kind of two programs for it, TGPN and TGP, whatever the name is not given yet. That's going to define operation in the more traditional 2.45 and 6 gig band and millimeter wave. So the first release of product, the mainstream Wi-Fi 8, will definitely be this TGPN type of operation. And so the objective is throughput at range, worst case latency and jitter, and it's going to be power saving enhancement, and for the first time there's also enhanced power modes for the AP side as well that's going to come, and peer-to-peer operation. So this is kind of the objective. I probably won't be able to detail more, but you'll see the slide. I've got a few slides on the technical solutions that are being proposed right now. But again, this is really the early stage, and this is what's going to keep us busy in the coming years. Russ, I think.
Right. Thank you, Laurent. Right on time, but we skipped some of the question. One of the first question Upkar asked was on 11AD-AY. I think this Wi-Fi 8. The comment probably addressed. Otherwise, please, folks, if your question is not asked and answered, please unmute and ask the question directly. Thank you.
Yeah, I have a question. In an enterprise or in a private network, is it that it is better to use 5G private or use 11BE?
Yeah, it's a good question. If you are able to operate Wi-Fi technology in an isolated environment without interference coming from other networks, you really are going to get amazing performance. Wi-Fi is extremely great in latency even today, and channel separation, all the scheduling tools we have makes it a great technology. So if we were to use the licensed band used,
I can't hear you.
Oh, you can't hear me anymore?
I can hear.
Yeah,
okay.
We can hear you. Carry on, Laurent.
Yeah. Okay.
Yeah, carry on.
So if you use Wi-Fi in private network licensed spectrum, like some people have been thinking about, you'll get really great performance. It's not necessarily going to be better, but it's going to be surely cheaper. That's for sure.
And until you get other people to come along, right? When you get that's the danger. So coming back to my question, which I put to you. AD and AY, when we move to TDD and TD, right, and time division multiple access, how's that going to coexist with ESMA-CA?
Oh, yeah, you're referring to the 11AY mode of TDD? Yeah. So very likely we're gonna not ignore, but not have the same requirement as coexistence that we had in the lower band. Because the goal is really to make sure that that becomes more of a mainstream penetration to the market, instead of being kind of a niche type of applications in the past, like this TDD or the type of deployment that was considered before. And so obviously with that, we cannot be forced to support ADAY technology, which was a very dedicated chip, pretty expensive. So we will have to keep it to the simplest form, and do then coexistence with energy detection is probably going to be the how it works. Obviously, the great thing is that first of all, there's not a lot of deployment so far, but if there are, obviously the range limitations make this problem be less of a problem, hopefully. And there's so much spectrum that you will be able to probably find some space where.
Right. At the moment, it's used in higher bands, so FR2 bands, 60 gigs and all that. So yeah.
Right. Yeah.
Thank you.
Yeah. No problem. Thanks.
Any other questions? Yeah.
Yes. A question on Doppler shift for many people are using Wi-Fi for drone operations. Drones are getting much faster. Is there any improvement in Wi-Fi for Doppler shift destroying the QAM constellation to accommodate motion of the station? This is something that I've never seen in a spec.
No, I mean you're correct. There has been some attempts a little bit in AX, but probably not with the speed that we're talking about with the drones here. But we try to improve a bit the mobility by putting some preamble and sounding more frequently in time. I don't think it's really implemented, but we've got some modes in the spec that allows to do this to enhance the tracking. But really going into very, very high speed, like you're mentioning here, so far has not been mentioned. And so I assume it's mostly proprietary solution that are doing that right now.
Could I, Laurent, can I just add to that?
Sure, yeah.
So Daniel, is it Daniel asking the question?
Yes, it's Daniel. Go ahead.
Yeah. So you have to look at the evolution of 11p. You have to look at DSRC, and that fork is what you should be following, rather than this AX fork, right? The V2X fork, if that helps you, and follow up with me later on. I'll give you more clarity.
Thank you. Now this is for being able to have robust communication under Doppler shift, not so much for localizing the client. Is that still in the same? Are we talking the same thing?
No, 11p is vehicle-to-vehicle communication, DSRC. That's mass communication with nodes that are moving.
Oh, great. Good.
The nodes are moving at fairly in 2D, but there is interest to having highest Doppler and then in 3D as well.
Thank you.
Yeah. And the one that I mentioned in AX was basically reusing some of the features that were defined in 11p, but for the mainstream bands. But yeah, 11p is definitely a good example there. Yeah.
All right. Okay. If there is no other questions, we can thank our speaker. Thank you so much for a wonderful talk. Very informative, and thanks for doing that. In your very late in the night time.
No problem. Yeah, it was a pleasure to.
Thank you. So Laurent,
Thanks.
please share your slides, and Pradeep will put it in that our website so others can look at it. Thank you so much.
I will.